So let me now ask you to do another thing. Which one are we looking at now? I want you to go to number 3. In case of number 3, the function itself is a scalar. The function itself is a scalar. But its argument is a tensor. Do you know anything like that? Is there anything you are familiar with? The argument is a tensor, but the function itself is a scalar. I want you to go and tell me if you know something. Okay, let me just type the question. Can you tell me anything you have come across? No? Stress, let us see. In case of stress, the argument is a vector and the function is a tensor in the case of stress. Because the stress is defined from point to point and it's a tensor. Ajibola, do you agree with me? The stress changes from point to point. And the stress itself is a tensor, but this argument is a vector. The stress field is a tensor field. I want us to just stay at number 3. This thing itself is a scalar, but its argument is a tensor. I will give you at least 4 examples. And all those 4 examples are things you know. So I want you to give yourself another effort. The trace, Kamal, the trace. Great, Kamal. The trace, the determinant. Great, Israel. The determinant is a scalar, but its argument is a tensor. More. So Kamal has got something. Israel has got another one. Magnitude of a tensor again, yes. The trace of a cofactor, of course. Correct. Let's see one more thing. Oh, okay, you've given me all. The determinant, the magnitude, the trace, all the principal invariants fall into the category 3. So, inner product is not, inner product is not, inner product is an operation. So, dot product is an operation. Can somebody give me an example of a function whose argument is a vector and whose value is also a vector? Can you give me an example of something? Can you give me an example of something whose... Can you give me an example of number 4 now? Can you give me an example of something that produces a vector value and whose argument is also a vector? The value of the function is a vector and its argument is a vector. Can you give me an example of that? No? 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 We are getting to number 4. I think this is very rewarding because, well, let me type the question again. Argument is vector. Function is vector valued. Argument is a vector. The function itself is vector valued. No, gradient is not magnetic field. No, magnetic field. Yes, Ajibola. I didn't even think about that. You are correct, Ajibola, because in a magnetic field, at every point, there's a magnetic force. That force is a vector, and there is a position vector at that point. So it is a vector function of a vector domain. Ajibola, great. Good, Ajibola. So a magnetic field is a case of number 4. It's a case of number 4. It's a magnetic field. That's a good point. Any other person? I will give you other examples because the one Ajibola gave is I wasn't even thinking of it. Can we get any other example? Magnetic field. Any force field. Example, gravitational field, where you are sitting down, is a case of a vector function of a vector domain. Any force field is like that. Any force. It doesn't matter whether it's magnetic. Of course, and Gochuku, of course, an electric field is like that. An electric field belongs to category 4. An electric field is like that. Electric field, magnetic field, anytime there's a force defined as you are moving from point to point, the gravitational field is correct. I still have other ones that we have not talked about. Nobody has talked about. I want to see whether anybody will see. Fluid flow. Great. James will not talk. Great, because fluid is flowing. At every point, for instance, a velocity is defined. And that point, there's a position vector at that point. An acceleration is defined. And there's a position vector for the acceleration. All those ones are vector function of vector domain. Fluid flow is a good example. It's fluid velocity in fluid flow, acceleration in fluid flow, even position in fluid flow. So all those ones are functions of a vector field, and the functions themselves are vector functions. Okay. So the fluid flow was what I had in mind to tell you about. So the velocity of a flowing fluid. But anytime there is a velocity, there's a force, there is acceleration, all of that belongs to category 4. Now, category 5, let me put the question again. Argument is a scalar. Function is a tensor. And somebody give me an example of category 5. The function is a tensor, but this argument is a scalar. Can anybody give me an example of that? Kamal, you are wrong. Outer product is a product, it's not a function. James, without tongue, you might be correct, but there is something wrong. There is something that is not fully explained in your answer. Inertia tensor. Yes, that might be correct, depending on something. Okay, Ginika, no, the examples you are giving are completely erroneous. Let me tell you, if you have a tensor that is time dependent, something that is changing with respect to time. For example, if in a particular situation, the stress at a particular location is changing from time to time, so that stress is a tensor and is a function of time. Time is a scalar quantity. So because time is a scalar quantity, it is time that is determining the value of the tensor. So it's a scalar argument and the tensor value. So any time-dependent tensor or time-dependent vector can be a situation where you have a tensor which is a function of the scalar value. So the next thing is, if that is clear, let me go to the number 6. In number 6 case, we have argument is argument in number 6, argument is vector, function has tensor value. Can you give me thermal conductivity, thermal conductivity is a scalar quantity that can have can vary from point to point. It will be an example of number, thermal conductivity will be an example of number 2. There is a scalar function of a vector domain. Okay, so we are now in number 6. Can you give me an example of number 6? A tensor valued function that, no, the two examples are not correct. Yes, I am happy, Adibola Matthew, that you remembered. Yes, because if you have stress in a particular place, and the stress varies from point to point is a position vector, and the value is a tensor. Strain is moving from point to point is position vector, which is the argument, but the value is also a tensor. Even displacement is moving from point to point, changing from point to point, and the location is also a position vector. So displacement. So everything when you do your stress analysis and you do your simulation, all the things that are given to you are in category 6. Now, the big one, I don't know whether I even have an example here. When the function is a tensor and the argument is a tensor, I don't have an immediate example. Let me see if I can think of an immediate example. Wait, maybe you can, but let me just see. I will do the thinking with you. Tensor argument. Tensor function. Tensor valued function. Yes, I have an example. So, can you find an example of that? I want to see if somebody in the class can find it. I have one example. There may be more, but one example is already in my mind. The Jacobian matrix. The Jacobian, let us see. Jacobian is a scalar. No, Jacobian falls into category, let's see what category that will fall into. Is category 3. Yeah, is it category 3? No. Scalar and vector. Category 2, I think. Ajibola Matthew, again, you got it. That's it. The cofactor is a tensor and is a function of a tensor. The cofactor of a tensor is a tensor function that is defined in the tensor space. Boluwatife, you are correct. The inverse of a tensor is a tensor function of another tensor. So, homework assignment for the class, and it should be submitted. When? The homework assignment for the class, this particular homework assignment should be submitted to your class rep by Friday, and he will pass it to the admin. So what you are going to do, you are going to go through and give 2 examples on each of these 7 categories. There's one category missing. Let me see whether somebody can tell me one category that is missing, because there should be 8 categories, I think. There's one category missing. Abdurrahim, You are correct. The transpose is a vector, is a tensor function of a tensor variable. Yes. The trace of grad. Israel, that one pass me. Tensor argument scalar value. Okay. What I'm trying to do here, let me give you what missing category. And somebody tell me what category is missing. There should be 8 of them, as I can see. No, it's not, that's not missing because that is number 1. Babalola, that's number 1. No, tensor argument and vector value. Let's see. Tensor argument and vector value. Tensor argument and vector value. Oh, if that is missing, tensor argument and vector value. Yes, who said that? So that means that we have more than one missing. That is Kamal. That makes 2 because there's something else I'm looking at. Argument and vector value. Scalar argument and vector value. Scalar argument. Yes, that's the one I was thinking of. Olamide. So there will be 9 categories now. So your homework, let me type the homework here now. So your homework, there are 9 categories we have already established. So you will just carry this table and fill in the blanks. That is, you are going to put categories 8 and 9, and you are going to put the Gateau-Freche example of all of the 2 that you are adding. And that's it. And submit that on Friday. Today is Wednesday. Yes, today is Wednesday. So submit that 2 days time. I don't want it to be too long because I want you to quickly submit it. And I'm going to give 5 marks, 5 final exam marks. Final marks will be attributed to that homework. So you do it and submit. Oh, but you are going to copy each other. So how am I going to? If you copy, how are you sure the person you are copying is correct? Well, so the 5 marks will be for 1 mark for the category, 1 mark for each category, 1 mark for each example. So that's it. So there will be 5 marks. So I want you to do that. Okay. So this therefore tells us what we are talking about. Let us now see what we are talking about here. Here, we are looking for the derivative of a scalar with respect to a scalar. Here, we are looking for the derivative of a scalar with respect to a vector, because the function is a scalar and the argument is a vector. So we are saying that the derivative of a scalar with respect to a vector is itself a vector. So the temperature gradient is a vector. Here, we are looking for the derivative of a scalar with respect to a tensor. And we are saying that the derivative of a scalar with respect to a tensor is a tensor because it's a tensor that will be in an inner product to produce a scalar. This quantity must be a tensor. So the derivative, for instance, of the derivative of the determinant of a tensor with respect to the tensor is actually, you'll be surprised that the derivative of the determinant is actually the cofactor. That's something that will shock you. You differentiate the determinant with respect to the tensor, you are going to get the cofactor. Okay, the derivative of a tensor, of a determinant, which is a scalar, with respect to the tensor. Here, we are talking of the derivative of a vector with respect to a vector. An example here would be the velocity gradient, because the velocity of a flowing fluid is a vector, and the argument, the domain where it is flowing, is a vector. So who can tell me what this quantity would then be? Grad of the velocity gradient is the grad of the vector field. What will it be? What's the velocity gradient? What kind of quantity will it be? The velocity gradient. For you to check, you can see that the product we are having here is something operating on a vector to give you what operates on a vector to give you a vector. What kind of thing operates on a vector and it gives you a vector? What kind of thing is that? What is it that operates on a vector to give you a vector? A tensor. So that shows you that the velocity gradient, even though velocity itself is a vector, velocity gradient is a tensor. Okay? Here, when you differentiate a vector with respect to a scalar, it is still a tensor because you are just this ordinary multiplication here. And then this is the number 6 is a tricky one. You now have the gradient of a tensor. When the gradient of tensor, what kind of quantity is the gradient of a tensor? What kind of quantity is the gradient of a tensor? Yes, Israel Olaoye says it's a tensor. Correct. Correct. Am I correct? Grad tensor. Okay, so it's a third order tensor. This one is a difficult one. The grad here, when you have a tensor function of a tensor argument, what is this quantity here? If S is a tensor, if what you are differentiating with respect to is a tensor, what kind of quantity are we talking about here in this last one? Tensor valued function differentiated with respect to tensor. What kind of thing were we talking about here? What is this quantity? What kind of quantity is this? Moses says it's a tensor. It's a tensor, but of what order? Of what order? So where in a situation where the function is a tensor and the argument is a tensor. Emmanuel Olamide Boluwatife, you are all correct. Emmanuel said it's a fourth order tensor. Olamide says it's a fourth order tensor. Emmanuel says a fourth, Boluwatife says a fourth order tensor. Ogojuku, you are wrong, saying it's a second order tensor. You are wrong. This has to be a fourth order tensor. This quantity here is a fourth order tensor. Okay. Okay, good. So you go and now, I hope I defined the problem correctly. I hope you understand the question that is your homework. Have I written it out? No. Let me write it out. Homework. complete, the homework is to complete the table and find 2 examples each. Complete the table and find 2 examples each. James Udotong, you said you want an explanation why it should be a 4th order tensor. Well, because you are contracting grad. If you are contracting it on the 2nd order tensor to get a 2nd order tensor, then it has to be a 4th order tensor, because S here is not a vector. You see, all you need to remember, James, is that S here is a tensor. You are contracting it on a tensor to get a tensor, so it has to be a 4th order. If that is difficult for you, you will just note it is, but I will try and see how I can explain it further for you. That's where I will stop today. Unfortunately, I will still start here because I didn't get as far as I wanted to get today. So I would still leave it because I cannot give you your full class today. I have something to do that makes me need to leave you now. But this table that we have looked at is a worthwhile effort. In fact, with this, most of you who didn't understand before, I'm sure by the time you now see what we are doing here, where I said by the time you see what we are doing here, when you compare this, when you see what we are doing as a generalization of this, where we do not predict that we know the order of the differential and or the value of the function, whether it is function is a scalar or vector, and then we now want to find its derivative with respect to this. Well, so this is the generalization. We call that derivative grad. The grad can mean many things depending on what the thing is. So that is the generalization, and this is the way we define derivatives now, when we are no longer talking of scalar to scalar. When we are talking of scalar to vector, scalar to tensor, tensor to vector, tensor to scalar, tensor to vector, and so many things, any combination. So that is the way we are getting the generalization from this well-known relationship, so that we are no longer talking of division. We are generalizing from this well-known relationship. So try and disabuse your mind of the fractional interpretation of the derivative, and you will now see that from there, once you get to that level, you are dealing with what they call Frechet derivatives. And the Frechet derivatives now move you from the elementary math you have to the higher ones without any break. And that's it. So I will continue. I will still spend one more lecture on this, but I am quite content today because I think I got the class engaged. All the other time I was almost getting depressed because the class was just no longer as excited as it used to be. But I think we have gotten our mojo back now. So we will move on in next class. So class, thanks for your attention, and I want you to go now read this whole thing, read the whole note with the mind that you got today, and I think you are going to be at a different level, and you are going to be acing your self-test much more easily now. So thank you, and admit, please, you can close the lecture.